Okay, we're ready for another presentation here. This presentation is meant to give you a couple of more examples of Newton's laws problems and also to more formally introduce friction and the way we're going to calculate friction. So we'll get started with a classic example here. This is a pulley problem. And the idea of this problem is with my crude drawing here, you're picturing a pulley with two masses hung on it. And we'll assume that the mass number 2 is more massive than mass number 1 here. And we can picture that there's going to be some motion in the masses. They are going to be moving in this direction with mass number 2 pulling it downward and mass number 1 being pulled up. That makes good sense. Now, for this example, we're going to assume that the pulley itself has no mass and that there's no friction. So here we're still working without friction. Okay, so a good starting point on this would probably be a free body diagram. We've talked about those free body diagrams. So here I am including the tension in the string that connects them on the pulley. Now, the tension will be the same. It's the same string, so I'm just going to call it T. I'm not going to distinguish between the two different tensions here. So the tension is pulling both masses toward the pulley. And that's not the only forces that are acting on the two masses. There is also, of course, gravity. So for mass number 2, there's gravity pulling down and then the tension resisting that motion. And for mass number 1, there is the tension pulling it up and then the weight, m1g, resisting it in the other direction. So here I have a free body diagram that identifies the forces working on both of these masses. Okay, so what I'm going to do now is I'm going to try to come up with an equation. Because you know in the problem, I've asked you to find the acceleration and the tension. And actually what I'm doing here also is I'm having you do it in terms of variables. So I'm not giving you a number to work with right now, but I'm asking you to come up with a general formula. And that's something that you should always be prepared to do. Okay, so since mass number 2 multiplied by gravity, its weight here, is greater than the tension, I am indicating here for mass number 2 the sum of the forces acting on it. So its weight pulling down minus the tension is going to be that mass number 2, multiplied by its acceleration. So here I'm just applying Newton's second law to mass number 2 with my free body diagram and indicating the sum of my forces. Similarly, I will do that for mass number 1. Mass number 1 here also has a Newton's second law applied to it. And this time the tension is bigger, pulling it up, so the tension minus the weight is going to be mass number 1 multiplied by its acceleration. All right, presumably I would know what mass number 1 and mass number 2 is, but here I have a very generalized formula of what's going on. All right, I'll take it a little bit further for you here, and let's see if you can take it to its conclusion. So here what I'm doing for mass number 1 is I am getting the tension isolated by itself. Now I've got a variable here, and I've indicated it in red. I've got a variable for tension here that is in terms of some other terms, getting us closer to what we were trying to do for this problem in the first place. Now, I've done this in red because what I want to do is I want to substitute that over here for tension. And when I do that, I want to show it to you in red so you can see what's going on. All right, so here I am substituting in for tension. In red, what I found out was equal to tension. So what I've done here in this step, and this is as far as I'm going to go here, is I've given you a way of putting acceleration in terms of the two masses and the acceleration due to gravity. So once you have acceleration, you can plug that back in here to find the tension because you'll have all of the other information. So I hope that was informative. and that it made some sense to you. But this stuff can be confusing. So if it was, please ask about it in class, and we'll definitely discuss this when we get back together. Okay, so if you're trying to do this with numbers, now again, you should be always prepared to do this in terms of symbols, but just to see if you got the idea here to build your confidence, what happens if mass number 1 was 5.00 kilograms and mass number 2 was 8.00 kilograms? Well, give that a try if you like, and then come back. I'll give you the answer. Okay, you're back. How did it go for you? Here's what I got for the acceleration and for the tensions. So if you didn't get those numbers, then, ask about it in class. Maybe I got it wrong. Maybe you can tell me where my logic fell apart. And if we got the same answers, then that's a pretty good thing too. But either way, you'll boost some confidence in what you're doing here. Remember, please, always to take what we're doing and try to think about where it would be going, where the next steps would be. All right, here's another type of question I could ask. This is example number 2 in your notes. And I'm asking here about two masses on a frictionless surface, and I'm going to assume that they're pulled with a force of F. So what I'm asking you to do here is to find the acceleration and also the tension in the string between them, because there would be a tension in the string between them as well that would cause the two masses to move. The pulling force and then the tension between them would cause mass number 1 to move. So, can you find the acceleration and the tension in terms of M1, M2, and F? So there's your challenge to do it in terms of the symbols, something that you should be prepared to do. But I know it can be challenging. But why don't you give that a try? I'll show you what I got after you come back, and if there's any problems, of course, we can discuss it in class. It's an interesting discussion to have. Okay, you're back? How did you do? I reduced it as far as I could, and I came up with these values. This was my value for acceleration and my value for tension. And I think I got that right. Well, anyway, let's discuss it in class. Let's see what you got. Let's see what I got. All right, so here is example number 3. In the last video, I spent some time talking about how gravity is different on an incline, and this problem ties into that one. Again, we'll assume a frictionless surface, and let's just assume we have a block, a mass, let's say, that's being pushed up the incline here. And this time, let me give you a number, just for switching it up a little bit, let's say. And let me say the initial velocity was 5.00 meters per second. So my question is, how far up the incline will the block go before it comes to a rest? How far will it go? All right, well, see if you can do that. And when you come back, I'll give you my answer. Okay, you're back? All right, well, I came up with 2.55 meters. How did I do? How did you do? Well, let's discuss it in class if you have any questions, and we'll see if we're in agreement on that one. Okay, always you should be thinking about what's the next step here? Where could we be going with these things? So now where I'm going to go is talk about friction. So far maybe friction has been in general terms. Now we're specifically going to make calculations for friction. So let's discuss it and how those calculations will come about. It should make some sense with friction that friction is related to the normal force. Friction is going to be the interaction between two surfaces. So the normal force, that support force that the surface pushes back up with, that perpendicular force that we discussed in the last video, is going to have something to do with it. And you should go back to your notes maybe to see all the different ways we talked about normal forces in that first video. Okay. So the friction is the normal force. The force of friction is going to be the normal force, so these are measured in newtons, multiplied by a coefficient of friction. Now, this coefficient of friction is the italicized letter U, or actually the Greek letter mu. So the coefficient of friction here is mu. That's what they call the coefficient of friction. And that value depends on the surfaces that you're dealing with. If you have a slick road, you're going to have a smaller coefficient of friction than if you have a dry road. And I'm talking about the interaction between a car's tires, let's say, or a bicycle's tire for that matter, or your shoes for that matter. But the coefficient of friction depends on the two surfaces. And this number is one of the numbers in physics that does not have a unit to it. So friction will be measured in newtons because the normal force is measured in newtons, and there's no unit at all for the coefficient of friction. Now, friction can be static, meaning, it takes a little effort to overcome something that's sitting still. And when you're overcoming something when it's sitting still, you're overcoming the static friction. So U, or mu if you prefer, with an S here indicates that the object hasn't started moving yet. And, well, are you already thinking of the next step? That's what we should be doing every time, trying to think of what's going to be coming next. How could it be built upon? So kinetic friction is going to be the other one. Once you start moving, you're using the coefficient of kinetic friction, which is different. You may have noticed that if you try to get a heavy object moving across a floor. It takes a little bit of effort to get it moving, and once you get it moving, it's a little easier to push it. Has that been your experience? Well, give it a try. Push something around the house. Got a little brother or sister? No, don't do that. Don't do that. But the kinetic friction is always, the coefficient of kinetic friction for two surfaces will always be a little bit less because it takes a little bit more to overcome the static friction. Okay, so we can see it's related to the normal force, and again, I will remind you, go back to your notes from the last video. We talked about the normal force in a lot of different ways in that video. Okay, so another thing that I want to mention is that friction is a reactionary force. So yeah, the normal force multiplied by the coefficient, but if you push with less of a force, friction isn't going to push back at you with a bigger force. So friction is a reactionary force, and it will only give as good as it gets. Usually we think of friction in terms of a resistive force, but it will keep giving as much as it can until it's given the maximum amount that it can. So on the AP exam and on the formula sheets that I'll give you for the test, it's going to look something like this, where FF is the force of friction, and that's an absolute value that they're talking about here, and that'll be your less than or equal to the mu, the coefficient of friction, multiplied by the normal force. So here with the less than or equal sign, they're saying that friction, this is the maximum really, the normal force multiplied by the coefficient. This is the maximum force of friction available to you. But if you give less of a force, an applied force let's say, then friction will only give as good as it gets. Well, hopefully you're thinking, where is he going to go with these calculations? And that'll be something for probably our next class meeting. So I hope you enjoyed today's video. Hope it was informative, and look forward to seeing you back in class with any questions that you might have from this video or any other questions that you might have. Okay.